All right, Chemistry Lab week 2, example problems. So luckily, the way I set this one up, this is for a different session, different thing, a year-ish ago, a little bit over a year actually. And all the example problems are just smacked at the end. So it's going to be increasing in difficulty from the Regents level, chemistry regions, all the way to US NCO, locals, nationals, I forget. All right, so let's just start with the very basic one. That'll be slide 25 for when you get this. So when the equation, we have that equation silicon oxide plus carbon goes into silicon carbide and carbon monoxide is correctly balanced using whole number coefficients. The sum of all the coefficients is, well, first let's figure out the balanced equation. 2 plus C goes into C. All right, so first, let's just balance the silicon first. Everything looks fine here. So we're fine with the silicon. Let's just leave it at that. Let's look at the carbons. Okay, so then on the product side, we have two carbons with carbide and the carbon from the silicon carbide and the carbon monoxide. That's 2 moles. But on the left-hand side, the reactant sides, there's only 1 mole. Well, let's fix that by adding a 2 over here. All right, so then that fixes that. So then let's look at the oxygen. So then on the right-hand side, there's 1 mole of oxygen. On the left-hand side, there's 2 moles of oxygen because that's silicon oxide. Let's fix that. Let's make this 2 so that we can balance out the oxygens. So then let's double check we have everything balanced. So then so the silicons didn't change at all. On the left-hand side, the reactant sides, I have 2 moles of carbon. On the left-hand side, I have 3 moles of carbon now. Let's fix that by changing the reactant side carbon from 2 to 3. So that way I have 3 moles of carbon on both sides. All right, let's double check everything. So then when it comes to silicon, well, I have 1 mole of silicon on both sides. And when it comes to oxygens, I have 2 moles of oxygens on both sides. When it comes to carbon, I have 3 moles of carbon on both sides. Okay, now am I done with the question? No, I am not done. Let's read the question one more time. When the equation is correctly balanced using whole number coefficients, I have whole number coefficients, the sum of all the coefficients. So I need to find the sum now. So if I take 1, so then if there's no coefficient in front of a compound, that's just automatically 1. So if I have 1 plus 3 plus 1 plus 2, that's going to be 7. That's our answer. Next one will be slide 26. So base your answer to the following question on given the balanced equation. I got sneeze. Ah, bless me. Thank you. So then based on that equation, butane reacts with 13 moles of oxygen, which gives me 8 moles of carbon dioxide and 10 moles of water. What is the total number of moles of oxygen gas that must react completely with 5 moles of butane? So this is the equation I have. And they're all gaseous. I'm not going to write that in though. All right, so this is just simply a dimensional analysis problem. So then I have 5 moles I'm given of butane. So then from here, well, I'll put 2 moles of butane on the bottom. And then we need to figure out the amount of moles of oxygen we have. So then I will have, or the amount of oxygens I need. So then based on this ratio over here, which is based on the left-hand side, that's going to be 13 moles of oxygen over here. So get rid of the moles over here because of dimensional analysis. And that becomes 32.5 moles of oxygen needed. And that's that. Pretty simple. Regents level is not very hard. All right, 3. Slide 27. So aluminum sulfide reacts with water to form aluminum hydroxide and hydrogen sulfide. A, write the balanced chemical equation for this reaction. All right, first let's figure out what these names are. It's a good thing we went over naming compounds in the first session. So aluminum sulfide, well, I have Al and S. Well, aluminum gives off 3 and sulfur needs 2. So then I'll have Al2 and S3. solid. I'm assuming it's going to be solid. It reacts with water to give aluminum hydroxide. Remember, aluminum is +3, so then it's going to give 3 electrons. Hydroxide is -1, so then to balance that out, I need 3 of these hydroxides. I believe that's solid. Yes, it is solid. And hydrogen sulfide. So that's going to be H2 because of +2, and then sulfur is -2, or sulfide is -2. So then that cancels out to 0. This is not balanced yet. So let's start balancing things. So then let's start addressing the aluminium. So then on the left-hand side, I have 2 moles of aluminium because of this subscript over here. So then I'll add a coefficient of 2 in front of this aluminum hydroxide to balance that. What else do I need to do? The sulfur. On the left-hand side, I have 3 moles of the sulfur because of this subscript. Let me do this in green. It's just a little more obvious. So because of this, I need to add 3 over here. And let's balance out the hydrogens and oxygens. So when it comes to the hydrogens, I have, well, 3 moles of hydrogen sulfide, but each hydrogen sulfide has 2 inside of it. So then that becomes 6 hydrogens over here. On this side, well, I have 2 moles of aluminum hydroxide, but each aluminum hydroxide has 3 OHs. So then this becomes 6 O's and 6 H's. So then on this side, I have 6 O's and 12 H's. Remember, the H's add up. Well, how do I fix that on the left-hand side with the waters? Well, luckily for me, the O's and H's are in a 1:2 ratio, or 2:1 ratio, because I said H first. So then I can simply fix that by smacking a 6 in front of the water. Because what happens here is that this 6 will multiply with this 2 to get 12. Good here. And the 6, well, there's only 1 mole of oxygen and 1 mole of water. So then that's going to be 6 over here. I'm balanced. So then that's that part over there. Now moving on to part B. So this is part A. Moving on to part B, how many grams of aluminum hydroxide are obtained from 10.5 grams of aluminum sulfide? Well, let's figure out how many moles of aluminum sulfide I have in the first place. Because when it comes to stoichiometry, let's work with moles, please. So 1 mole of aluminum sulfide. I'll spare you the math. That's going to be a molar mass of 150 grams. The grams cancel out, and I'm left with 0.07 moles of aluminum sulfide. Okay, so then I'm not done yet because I need to find out the amount of grams of aluminum hydroxide. So then if I did some dimensional analysis, so then if I go to the top over here, our balance equation is that. So then the ratio we'll have is going to be 1 mole of aluminum sulfide or 2 moles of aluminum hydroxide. So the moles of aluminum sulfides will cancel out, and I will have 0.14 moles of aluminum hydroxide. Am I done yet? No, because if I read the question, it asks for amount of grams. If you don't read, you are doomed. So let's figure out the amount of grams I have. So again, this is another dimensional analysis. So 1 mole of aluminum hydroxide is 78 grams. So I'm going to put 78 grams on the top because I want the moles to cancel out. Moles cancel out because they're both in the numerator and denominator, and I get a total of 10.9 grams of aluminum hydroxide. So that's going to be my final answer. I'm recording, right? Thank goodness. Next one. Let me change my color because I'm starting to get a little bored. Does yellow work here? It does. Ooh, works quite well, actually. I might use yellow now. Yellow, yellow, yellow. So a piece of aluminum foil of 0.55 millimeter thick and 1 centimeter square is allowed to react with bromine to form aluminum bromide. So the first question is, how many moles of aluminum were used? The density of aluminum is 2.699 grams per centimeters cubed. All right. So first of all, let's figure that out. How much aluminum do we have in the first place? So part A, 0.55. So this is slide 28. Millimeters, well, let's convert that to centimeters. So the centimeter, so all the units are going to be the same. That's going to be 0.055 centimeters. And if you know the volume, that's just going to be area times the height or thickness. I'll use H here. So we know the area because it gives us 1.00 centimeters squared. And guess what? If we have the height or thickness 0.055 centimeters, that's going to give us centimeters cubed, which is the unit in volume. And thankfully, because it's 1.00, we get a volume of 0.055 centimeters cubed. Okay, now we're not done yet. I just found the volume of this aluminum foil, but I need to find the amount of moles that were used. How do we do that? Well, let's do some dimensional analysis. And we do that. Sorry, I'm having a brain fart right now. Like a really, really bad brain fart. Yeah, okay, sorry. So let's just take the density of aluminium, and we'll see that we can then figure out the mass of aluminum that I have. So the centimeters cubed will cancel out, and I'm left with the grams, which gives me, and I'm not going to round yet, I'm just going to write everything I have on my calculator, 0.148445 moles of aluminum. Am I done yet? No. Actually, I lied. Oh, sorry. I double lied. This is not moles, this is grams. Grams of aluminum. Am I done yet? No. Read the question again. It asked for the amount of moles, so I need to do one more thing. So then using dimensional analysis one more time, 148,445 grams of aluminum. Well, the molar mass, well, 1 mole of aluminum is 27 grams. So the grams cancel out, and I'm left with 0.0055 moles of aluminum. So then that's the answer. Moving on to part B. How many grams of aluminum bromide form, assuming that the aluminum reacts completely? I don't know why I keep on switching between aluminum and aluminum. It's very weird, but I don't know. First of all, let's figure out what kind of reaction we have in the first place. So given the original situation, aluminum, solid, because it is a foil, is reacting with bromine. And when people say bromine, they really mean diatomic bromine, which is going to be a liquid because bromine occurs as a liquid as a diatomic molecule. So remember that. Gives us aluminum bromide. So that's going to be a solid. So this is the unbalanced reaction that we have. Let's balance this first. So let's see over here. Well, the bromine is the part that's really messed up. So let's fix that by smacking a 2 and smacking a 3. Oh, let me do this in a different color. Green. So I'm going to smack a 2 over here because of this 2 subscript. And using this 3 subscript, I'm going to smack that over here. Essentially, what I'm doing is that I'm just using the greatest common factor between 2 and 3, which is 6. Oh, sorry, not greatest common factor, lowest common multiple. So 2 and 3, that's going to be 6. So the bromine is all balanced, but the aluminum is not completely balanced. So let's fix that. And I can fix that by adding 2 in front of this aluminum over there. So let's just double check everything's balanced. Aluminum's balanced, bromine's balanced, we're all happy. Except me. Sorry, that was dark. So let's figure out the rest of the problem. So taking my answer from part A, where I have 0.0055 moles of aluminium, that's going to react with 2 moles of AlBr3 and 2 moles of Al. Well, moles cancel out, but because it's a 2-to-2 ratio, that's just really 1-to-1. That's really going to be 0.0055 moles of aluminum bromide. We're not done yet because it asks for nanograms. Don't stop here. The race is not over yet. So 0.0055 moles of aluminum bromide. Well, the molar mass of that is that in 1 mole of aluminum bromide, I'm going to have, and I'll spare you the math, 267 grams of this thing. So moles cancel out, left with grams, and I'm left with a final answer of 1.47 grams of aluminum bromide. So that is the final answer. Next one. So next 3 slides, these are the USNCO problems. Let's take a look at them. Let me transition to green. All right, so iron 3 oxide react with excess carbon monoxide at high temperature according to the equation below. So the equation below that we're given is Fe2, this is balanced. If 6.5 grams of Fe2(3) yields 3.85 grams of Fe, what is the percentage yield of the reaction? Okay, so let's figure out the amount of moles that we should have had in the first place. So 6.5 grams of iron 3 oxide. Well, how many moles is that? Well, 1 mole of Fe2O3. I'll spare you the math. That's 160 grams. That's the molar mass. Grams cancel out. And we're left with, I'm not going to round yet, 0.040625 moles of Fe2O3. So let's figure out the amount of iron we should have gotten. So using that value, 0.040625 moles of Fe2O3. Looking at a reaction over here, we're going to put, 2 moles of Fe for 1 mole of Fe2O3 that is derived from the ratios over here, 2, 1. And the moles of iron 3 oxide will cancel out to give us 0.0812 moles of iron. Well, what is that value in grams? 0.08125 moles of Fe. Well, 1 mole of Fe gives has 56 grams. Moles of Fe cancel. It gives us around 4.55 grams Fe. So this is the theoretical yields. Theoretical yields. So then we see inside the question that we had a yield of 3.85. That is our actual yield. So then to figure out our percentage yield, we have 3.85 grams as our actual yield over our theoretical yield of 4.55 grams times 100%. This looks like an S. We get a value of 84.7%. So not terrible. Yeah, not terrible, actually. Yeah, not terrible. So then that is the first process, or the first question. Let's move on to the next question. Let me do a different color. Let's do yellow again. Excuse me. So hydrogen gas reacts with 5.00 liters of nitrogen gas under constant temperature and pressure conditions to form 10.0 liters of ammonia gas. Oh, that's a burp. What is the minimum volume of hydrogen gas required to produce this amount of ammonia? Okay, well, first let's figure out the actual reaction. I'll just spare you the time and just do this very quickly because I know this reaction by heart. You will too soon. It's a very, very famous reaction. Don't worry about the double arrows for now, but just know that that is the proper notation for that. All right, so then we're giving these values in liters. Well, don't we want to work with moles? We do, but this goes back to the liquids and gases unit. So PV nRT, and if we solve for N represents the amount of moles we have. Because we're given that we have a constant pressure and a constant temperature, P, R, T are essentially the constants, and V is really the only variable. So in this case, because everything else is the same except volume, which then determines the amount of moles, I can actually work this entire problem pretending that the amount of liters is indicative of the amount of moles I have. So I'll show you what I mean by that. So using dimensional analysis, 5.00 liters of N2, well, dimensional analysis, well, 3. So the mole ratio of hydrogen to nitrogen is 3 to 1. 3.00 liters of H2, 1.00 liters of N2. The liters of N2 cancel out, and I'm left with 15.0 liters of H2. And that's actually going to be my final answer. That is the minimum volume of hydrogen gas required to produce this amount of ammonia. Yeah, that's the answer. And because of this relationship, and we're given that temperature and pressure are the same, really the amount of volume or the volume is indicative of the amount of moles. So then I can just pretend that liters is just another measurement of moles in this case. But it doesn't work in all cases. It just does in this case because of the constant pressure and constant temperature. And if you're wondering, this is called the ideal gas formula. And R is another constant. So final question. I'll do this in red. Now, for this final question, yes, I can plug and chug. So element E reacts with oxygen to produce EO2. Identify the element E if 16.5 grams of it react with excess oxygen to form 26.1 grams of EO2. And I'm given 4 options, and yes, I can pick random question or pick each option individually and just pray one of them works, but I want to do this more methodically. So let's do that more methodically. So the more methodical approach is E, reacting with oxygen gas. Remember, when people say oxygen, they really mean O2. And I get EO2. Everything's balanced, so I don't need to worry about that there. So we're given 16.5 grams. So that's the amount of E we have in the first place. And then if we were to use the molar mass, so 1 mole of E has 6 grams of E. We don't know what this grammage is because that's the molar mass. If we know the molar mass, we know what this element is. We don't know what this element is. So then I'm just going to use X as a placeholder. So then the grams of E cancel out, and I'm left with 16.5 over X moles of E. Well, let's figure out the amount of moles of EO2 we get. So 1 mole of EO2, 1 mole of E, amount of moles of E cancel out. So then now I'm left with 16.5 over X moles of EO2. All right. Now let's figure out the amount of grams of EO2 we got. Or well, we already know, but we can set up an equation to figure out. So 16.5 over X moles of EO2. Well, if we can multiply that by EO2's molar mass. So I'll put 1 mole of EO2 on the bottom. And then when it comes to the molar mass, well, we know it has 2 moles of oxygen. So 2 moles of oxygen is going to be 32, because 16 plus 16, plus X. And that is the E value. So we don't know what X is, so I'm going to write it as that, grams of EO2. And this is going to give us 26.1 grams of EO2, because that is the number that we are given within the problem. And here we just have a algebra problem. So the moles of EO2 cancel out, and I'll distribute the 16.5 to the 32 and the X over here. So then 16.5 over X times 32, well, that's going to become 528 over X plus 16.5 over X multiplied by X. Well, I'm going to have an X on the numerator and denominator. Those X's will cancel out. I am left with 16.5. So then this is going to be 26.1. I'm going to omit the units for now, but just know that the final answer and all these units from beyond now are all in grams. So then if I start doing some algebra, this is just an algebra problem now. I'll start solving for X. 9.6, I just subtracted by 16.5 on both ends, and I do. Then X gives us 55, and the units will be in grams. 55 grams. Well, we know the amount of grams, and that is the molar mass that we're working with. Well, guess what? Guess what has a molar mass of 55 grams per mole? Magnesium. And magnesium is indeed the correct answer. All right. Thank you for coming, and I'll see you next time. Yeah. See ya.